we first start by the case of the bar problem that we used earlier on to define the work done. Okay, the work done. You have class after this? You have a class after this? 1 o'clock you have class? So you can stay longer, yeah? You don't have class at 1 o'clock, yeah? Do you have a class at 1 o'clock in your timetable? You have another assignment, but no. So you have to do assignment at 1 o'clock, yeah? Now, I want to derive this, okay? And this equation, class, you have to remember. It's just like the governing differential equation of 1D bar, you have to remember in theory of elasticity. This one you have to remember in energy method. Okay? Now, we start with the work done. Yeah? Earlier on, we have the work done, which is work done by the external load, which is equal to strain energy. And in general, it is 0 to E Fs d epsilon s. Okay, so this is the one that we start off with. Okay. Remember the F for this bar. Okay. This is F x, okay. And Fs des is integration is area under the graph of F versus E. Now this is in general, so the material property is not there. So now we restrict ourselves to linear elastic material. We restrict ourselves to linear elastic material. Okay. Now for Fs, in the notes, I think in the notes that you have, S is upside. Now I put it down here. Fs is equal to sigma xs multiplied with A. Okay. So this is just a relationship between axial stress and axial force. Okay. And we have the relationship of epsilon x s is equal to EAS661-8 equal to L. Okay. ES X ES. So this is the relationship that we have for Fs sigma xa and epsilon xs Es over L. Okay. So we substitute that into that equation. So we first get UP equal to we substitute first this one with this, which is A sigma xs. Then from here, DES is equal to, from here we make use of this relationship, DES is equal to L D epsilon xs. Here. ES is equal to L epsilon X, so DES is equal to L D epsilon XS. Now for this bar here, A is constant, L of course is the length of the bar, so you take out this AL here. Then you have this term, which is sigma XS D epsilon XS dx. Okay. No dx anymore, sorry. And here, from the limit of E, we change to epsilon x now. We change the limit. Previously, we relate to E, now we relate to this, so this one also changed to epsilon x from 0 to that. Now, what I would like to show here is this AL is volume. AL is volume of the bar. Okay. So UP is a strain energy. So these terms here is actually strain energy per unit volume. This strain here, this is strain energy, this is volume of the body of the bar. So these terms here can be understood as strain energy per unit volume. Okay. So this term here is strain energy per unit volume. Because this is volume of the bar, A multiplied with L, you get the volume. This is strain energy, so this becomes strain energy per unit volume. And it has a special name. Okay, we call them strain energy density. We call them strain energy density. And we use the symbol here, Vp. Okay, small Vp, strain energy density. What we call it strain energy density. And this is area under the stress strain diagram. Area under the stress strain diagram is strain energy density. That earlier today's lecture we talked about that. Okay, and here we show that why it is called strain energy density. Okay. So up until now, class, up until here, up until now, this has nothing to do with material. Nothing to do with material properties. Material properties only comes in if we see the symbol E, elastic modulus. Okay? Material property has not appeared here. But up until now, there's nothing to do with material properties. It can be elastic, it can be non-linear elastic, it can be any kind of material properties. Okay. Now, in our class, in our lecture here, we are going to restrict ourselves to linear elastic material now. Okay. So for linear elastic material, then we have E come in, elastic modulus. Okay. We have E coming in now, which is the elastic modulus. So that is the next thing that we want to look at. We restrict ourselves now to linear elastic material and see what happened to the equation of strain energy. For that, let me take away these. So when we want to relate to material properties, so which means the stress for linear elastic material, then we have the relationship sigma x equal to E epsilon X S. Okay. Now, class, the S here is only some intermediate value. Okay, so intermediate value, which we use in this example. So now, if we introduce this into here, which is the strain energy, which is equal to integration of 0 to strain X, sigma area under the stress strain diagram. Now you restrict ourselves to linear elastic material now, so you will get 0 epsilon X, E epsilon XS, D epsilon XS. Okay. So that is the thing that we are going to get. Okay. If you integrate this, now you integrate this now. Epsilon X, the epsilon X you are going to get. If you try to integrate that, so strain energy, if you integrate that, it becomes E, then half epsilon X squared, right? You integrate that terms. And this one become half E epsilon X multiplied with epsilon X. So this one become half sigma X epsilon X. So now strain energy density for linear elastic material, this 1D problems, it becomes half sigma X epsilon X. So strain energy density is area under the stress strain curve. Stress and strain curve. For linear elastic material, you have a straight line here. So this is actually the area of this triangle. This is the area of that triangle. So for linear elastic material, the stress-strain relationship is straight line, and the strain energy density is given by half sigma multiplied with epsilon. Yeah. So from now on, we restrict ourselves to linear elastic material. E, and this is the law, the Hooke's law that it satisfies. Now, if we substitute this, we go back to the definition of strain energy, the relation between strain energy density and strain energy density and strain energy. Okay. So strain energy is symbol is capital U. Then we have AL volume multiplied with the strain energy density. So AL multiplied with, for linear elastic material, we have this. Okay. Or this is E epsilon X. So this one become half AEL. So this E epsilon X, so EAL half, then epsilon X square, epsilon square, yeah? Epsilon square. So this is the equation for strain energy in terms of strain square. Now, if we relate the strain to elongation, if we relate the strain to elongations, strain is equal to elongation divided by L, then strain energy become half AEL multiplied with this E square L square. Or it becomes half AE over L E square. So here, strain energy of a bar, okay, of a bar which is linearly elastic prismatic bar of length L is equal to half. If we call that as K, this is axial stiffness, so it becomes half KE square, where K is equal to EA over L, and this is axial stiffness. It's like the spring constant of the bar. So strain energy of a bar, linear elastic bar, is equal to half the elastic constant, the spring constant, multiplied with elongation square. Okay. So if you relate this to spring, so spring is strain energy in the spring is half K delta square. It's the same thing. But the spring constant here in the bar is become the axial stiffness, which is EA over L. Okay. So this is the relationship that we want to start off with for linear elastic. So all our discussion from now on is linear elastic. Strain energy density is half sigma multiplied with epsilon for linear elastic, and strain energy is half K E squared for linear elastic bar, and if the bar is prismatic. So after your lunch, okay, you don't have class in the afternoon. So after your lunch, you will continue the journey, okay, to derive the equations. Okay, but I know you have assignment to do, so it's better to let you busy with your assignment. Okay, so I will see you next week. Okay, so I will stop here now. It is 12:59. Okay, so these are the equations that we derive, and we will make use of this equation to get for general bar this equation for strain energy. Okay. So that's all for today, class. Okay. I know you are going to have another class later on. Okay. So class, for those who are online, we will stop here. Okay. And I'll see you again next week. Thank you all. Yeah. Right. So I will end the session now. Okay. Thank you. Thank you, Zoe. Thank you.